On this episode of Embedded Insiders, Brandon and Rich discuss the global chip shortage and the difference between price gouging, tough luck, and a need for innovation. Then Rich sits down with Russell Klein, Program Director for Siemens EDA, who will be keynoting Embedded Computing Design's Virtual AI Day on September 9th. We all know we need AI at the edge, but can that edge be battery powered? Later, Tiera Oliver dives deeper into the chip shortage to discover what makes semiconductor manufacturing so complex and time-consuming. After learning the answer to that question, atomic-level deposition, she touches space with researchers at Argonne National Laboratories who are leveraging open-source AI to accelerate the process.
Hello and welcome to the Embedded Insiders. I'm Brandon Lewis, Editor-in-Chief of Embedded Computing Design, here with Rich Nass, who's the EVP and Brand Director of said property. How you doing, Rich?
I'm doing okay. Haven't been introduced as the said property before. That's a new one.
Well, I just don't want to repeat myself. I
am a creature of habit, you know. I like to hear the same thing over and over.
The only thing that's certain is that everything will change.
I'm not sure if I agree with that, but I'll let you go with it for now.
Really? You think everything's going to stay the same?
Well, some things stay the same.
Such as?
The requirement to pay taxes, the forthcoming... No, let's not go there.
Everybody dies? Okay.
Yeah, that's where I was going, actually. I think we know each other too well. Something that is new... I was at a friend's engineering company the other day, and he was telling me about the chip shortage. And I said, yeah, I'm aware of that. You know, we've been interviewing people, you know, we talked to some of the disties. He was like, I don't think you are aware of it. And I said, what do you mean? And he started telling me the story about how it's far worse than I was aware of and that the suppliers are letting on. They were building a board and they needed a buck converter. It is normally a 50-cent part. They need 10,000 of them. No one has them. They've tried every place and they just can't get them. They finally found a broker who had 6,000 of them, and he was willing to part with this 50-cent part for $6 a piece.
Mm-hmm.
I don't think I'm allowed to swear on the podcast, but that's BS, you know.
Oh, no, that's capitalism.
I guess, but and it wasn't just that singular part. In addition to that, micros were very, very hard to come by and in the same boat. A $8 part was going for $60, and I mean, it's just. And it snowballs down. Then I happened to be talking to somebody else, and we were talking about how it's moved into plastics. It's moved from automobiles. It's into boats. It seems to be just rippling into all other different areas, and all starting with semiconductors. And when I spoke to a distie a few weeks ago, maybe a month ago, when it would come back to normal, doing air quotes around normal, 2023. So if you're a designer, you're in a tough spot.
So when things like this happen, I always, ponder the legitimacy of everything, in terms of market, supply, demand. You know, a lot of times you'll hear about an oil pipeline bursting, that carries crude to some place or another, and then all of a sudden the next day our gas prices go up, and you're like, what the hell? That oil isn't destined for our fuel pump for another 3 months. But in this case, you're talking about massive global supply chains, and the problem with the semiconductor shortage is actually really interesting because it's multifaceted. It's not just what happened with COVID, and also it's not just what happened with the isolated incidents like fires at Renaissance Manufacturing, at fabs and stuff. A lot of this started several years ago when we started hearing about the MLCC shortage with the ceramic capacitors, and that was really because the MLCC manufacturers, so much margin had been stripped out of those parts that they're like, we're not going to keep making these things for half a penny a piece. We're going to start allocating some of our production capacity to these new, more advanced, higher margin devices. And it sort of left everybody in a lurch, while they're transitioning to this other stuff. So there are a whole lot of factors in play, and the people that really get hurt, you're right, are the designers at this point, and then subsequently the consumers. But I still don't know, does it really take 2 years for us to come up with a solution to this? Is there really only one mousetrap, for your buck converter, or is there not another way to design around it?
Well, the first lesson, without a doubt, is do not design in a single source.
Oh yeah.
Shame on you if that's the avenue that you're going. But in the case of a micro, you might not have a choice. In the case of a power component, you probably should.
Why don't you have a choice in the case of a micro? I mean, they're all ARM based, right? They're all 32-bit ARMs, it's all the same thing, right?
I think we discussed that on podcast number 37 in 2009, the difference between the various ARM processors. But no, an ARM is not an ARM. It's not an ARM.
The other side of the coin is how much of this is just straight up price gouging.
I honestly don't think that that's it. I really think that these chips are not able to be produced at the rate that they are. And of course, what we're talking about is a quantity of 10,000. If you're the guy who needs 500,000, you're a much better customer to the supplier, and you're going to get your supply first.
For sure. And also, when all this COVID jazz happened, they started allocating stock, to the different markets, to different companies. Yeah, if you're the low man on the totem pole, I guess the lesson is don't be the low man on the totem pole.
Exactly.
Which is tough. Going back to my point before, you said don't be single source. One thing that we know is that there should be innovation that comes out of situations like this, COVID in general, but out of shortages like this. It's a great opportunity for somebody to figure out a way, to circumvent your traditional buck converter or your traditional capacitor. And I know that, a capacitor is what it is. That's not like it's not like a novel part, but this is a great time for engineers to innovate, because they're, in a lot of cases, like your friends, looking for quantity 10,000 are going to have to. They're not, they can't wait until 2023 to ship their design, right?
Yes. And unfortunately, in their case, they're looking for NRE to keep the doors open and the lights on.
Right. Yeah. And that's a shame. So I'm going to make a logical leap here, but I want to talk about this. It's about
whenever you say you want to make a logical leap, you generally don't make a logical leap, but go ahead.
Okay. So I want to talk about standards a little bit, and it relates to this shortage in that, in a lot of cases, what we're talking about, the things that are not available right now are not components of a design that are differentiators, right? These are just basic building blocks that you need to make an electronic system. So we take that for granted a lot of the time. I was talking to some folks over at the Linux Foundation, and they're talking about all of these frameworks and all the stuff they're putting in place on LF Edge, and the umbrella of standards that they're working on that fall underneath that, to make things easier for IoT designers. Because, in their words, and to a large extent this is true, all of this is just plumbing. All of this is just infrastructure. Nobody's really innovating, in terms of your Ethernet file system, right? And I extended that during the conversation to operating systems, which is, how much innovation is left, again, air quotes, is left around your operating system. If you'd ask somebody at Microsoft, I think the answer is none, because that's what, they're wrapping in things like, Express Logic, ThreadX, and it's really treated now as just sort of a, an infrastructure component that you need, just sort of the way you need a capacitor, right? Do people really design operating systems anymore the way they did 30 years ago, as this is going to be the thing that sets us apart from the next guy, embedded or otherwise? That's
a pretty good point. And the obvious reason for that is that there are so few operating system vendors out there anymore. Mm-hmm. So the need to compete is not nearly what it was 10 years ago, when you could rattle off a dozen different operating system companies. And they're differentiating in very subtle ways, very application specific. Use this one because it's tuned for this very specific thing. That's a good point. And but the differentiation is happening in how you use that operating system more so than the operating system itself. The components are being fine-tuned for the OS rather than vice versa. You're not going to see some different version of Linux that's a step function ahead of what was out there before. So you tune your hardware to make that step function appear.
Right. I think that the big question that this raises, though, is, okay, yes, you tune the hardware, or yes, it's how you use the operating system in your various application. But have we built the best RTOSes that could conceivably be? I mean, an RTOS may be a bad example because by its very nature, it's supposed to be simple. It's supposed to be trimmed down. It's supposed to be really good at timing and scheduling. But is there no need anymore to build a better RTOS? Is there no need anymore to build a better capacitor or buck converter?
Well, I would definitely say that until an RTOS is actually RT, there's room for improvement. Yeah. And I assume that's an impossible goal, but we have to keep getting closer and closer to it, especially when we get into things like autonomous drive and healthcare applications, when RT is a situation of life and death.
Right. For sure. But again, what real time is dependent on who you ask, right? What's the value of my house? It's whatever somebody will pay for it, right? Same thing with what's real time. It depends what Boeing says, or what Rockwell Collins says, or what Kaiser Permanente.
Well, but you're not defining real time. You're defining the need for real time.
Correct. Right, but the need for real time is what's going to drive the development and the innovation of that technology, whatever the technology is.
Well, when your autonomous car hits a person and you say the OS didn't react fast enough, well, then you didn't meet your need for real time.
Right, correct. But until that happens, I think the answer is there is no innovation needed in them, because if there was innovation needed in them, then somebody would be contracting these RTOS companies and contracting, the capacitor manufacturers to make something that would be worthwhile to produce. So
I guess so. But again, I think that innovation is happening elsewhere other than the RTOS to supplement, augment, what's the word I'm looking for, to make those things happen irrespective of the operating system. Tesla's not sitting around waiting for some OS guy to say, hey, I can do this better. They're re-engineering to make that happen.
Does that mean that there's a space there for innovation?
You want to start an operating system company? Is that where we're going with this?
Yes. No, I don't.
I'm game. I can do that. I can write an operating system.
You want to start an RTOS company? Who's our big? Tell the guys at Siemens and Wind River they better watch their backs.
Absolutely. NAS Lewis OS. NLOS.
NLOS. That's it.
Next, Russell Klein previews his upcoming keynote at Embedded Computing Design's virtual AI Day on September 9th.
You are giving the keynote address at our AI Day event that's coming up shortly. The title of your address is Bring AI to the Edge of the IoT. That is a pretty generic statement, bring AI out to the edge. First of all, what do you mean by that? When you say bring AI out, what exactly are we bringing out?
Well, typically we're going to be bringing out inferencing. There are going to be cases where we're doing training on the edge, but I think most of the applications that we're going to see throughout industry is going to be inferencing. And as we know, inferencing is a hugely compute-intensive task. But the edge is comprised of a huge diversity of systems. It's everything from little battery-powered watch things to things that might have a 10 kilowatt generator on board. And so there's really not going to be one pat answer for, what does it mean to bring inferencing or AI to the edge? It's really going to depend on the system. So those systems that are really big and beefy and we've got a fat power line going into them, you're going to be able to drop in a really powerful CPU or an array of NVIDIA GPUs and go to town with inferencing. You're going to load up Linux, you're going to load up TensorFlow. It's going to work just like it does in the data center, and that's not going to be a challenge. But the edge is also comprised of these really constrained devices that might be hard to get to, that have really limited compute capability, that are on tight energy budgets. They may even be harvesting this energy from their environment. They may not have a dedicated power supply. And this is where taking that computationally complex inferencing and getting it to run on these types of systems is a really interesting challenge. So this is at least where my talk is going to go into a little bit of detail.
Okay, so I think you actually even answered my second question. Well, the first question is, does it make sense to bring these out or bring these out to the edge? And it sounds like the answer is it depends. So the second question, which you started to answer, and you started to go down that path. When I think of an AI system, I think of something that is very compute intensive. So when you say it depends, what does it depend on? I mean, is it just basically what the application is? And if it's my watch, then the answer is probably no. If it's more of something that's going to reside in my house, then the answer is yes. Is that where we're going?
No, I think we're going to see AI go into all kinds of these systems, right? So you used your watch as an example. The Fitbit that many people are wearing on their wrists and is probably smaller than the watch you've got on right now, that's got inferencing going on inside of it today, right? It's looking at a bunch of accelerometers and it's performing an inference to figure out, are you munching potato chips on the couch or are you running a marathon? And so this is going on today. And the real challenge is, how do we take what has traditionally been a very compute-intensive application and get it to fit in these systems where we want it to run on a battery for weeks or maybe even months? And that's the challenge. And like I said, that's an interesting area to go work in.
So are you saying we're going to do AI on a battery-powered system? Are you on record there?
I'm on record there. We could do this. And the real challenge is, how do we reduce the computational load that's going to take place as we're doing these inferences? Now, if you look at your power budget, you've got three really big items, and it is the storage of your weight and bias database, and these databases can be very large. You've got the movement of the weight and bias database to get it out to the computational elements, and then you've got the computation itself. Now, on different systems, each one of those items, you might have a different item on the top of your power consumption budget, but those are the big three. And so what you really want to look at is, can we take that weight and bias database and make it much, much smaller than it is when we when the data scientists first put together a particular inferencing algorithm.
But it always seems like we're moving in the opposite direction. While it's great to make stuff so smaller and smaller, it just seems like the lines of code gets bloated, and the number of sensors we need out there is, we always need one more. Are these two things working in opposite directions?
Oh, they're absolutely working against each other. What we're seeing, if you look at the winners of the various object recognition contests, those neural networks get bigger and bigger every year. But the reality is that it is possible to, through a variety of techniques, to shave those down significantly, right? And I'm not talking about making it 5% smaller or even 75% smaller. I'm talking an order of magnitude or 2 or 3, right? These algorithms, once they're figured out, can be shrunk down rather significantly to a point where they do become practical for these small embedded systems.
Okay, Russ, before I let you give away too much and not give people a reason to attend your keynote, we're going to cut it right here, because I know you're going to go into way more detail in your keynote, which is September 9th at 11 o'clock Eastern Time at AI Day, which can be found at ai-mlday.com.
Now, Tiera Oliver investigates how AI is automating portions of the semiconductor manufacturing process to get chips to market faster. The current global semiconductor chip shortage is causing a domino effect for global supply chains. Not only are the prices rising for newly manufactured cars, but all types of electronics such as smartphones, laptops, and more. As a means to slow down the shortage, researchers at Argonne National Laboratory, a U.S. Department of Energy national laboratory, have invented an AI-based solution that synthesizes semiconductor nanomaterials. Most chip manufacturers utilize atomic layer deposition, or ALD, a thin film deposition technique for creating very fine films to fabricate today's impossibly scaled down microelectronics. The technique involves a gas-phase chemical process where the ALD reactions use two chemicals called precursors and reactants. The precursors react with the surface of each material one at a time, then a thin film is slowly deposited through repeated exposure to separate precursors. ALD is an important process in fabricating semiconductor devices, but the downside is the lengthy trial and error process of making new films from each new material. For example, in order to identify optimal growth for each new material scientists must arrange the complex chemistries between the molecular precursors, figure out when each dose of each precursor needs to be added, and determine the appropriate reactor design, temperature, and pressure. Angel Yanguas-Gil, a principal materials scientist at Argonne National Laboratory and co-author of a recent ALD research study, explains,
"Each cycle of growth and thickness characterization typically takes a few hours, with the exact duration being dependent on the process itself. Variables such as the desired field thickness and the availability of characterization tools affect the process. For challenging ALD thin films, materials and precursors, it can take months to develop a working process."
Argonne National researchers are the first to use AI to automate this process. They are using 3 approaches based on Bayesian optimization, random, and expert system algorithms to offer various ALD film combinations for the different materials. The overall goal of these 3 approaches is to achieve the highest and most stable thin film growth in the shortest time using simulations that represent the ALD process inside a reactor. The Bayesian, random, and expert system techniques are tested by comparing how they affected the dosage and purge times of the 2 precursors used in ALD, where the dosage time is the time it takes to add the precursor to the reactor, and the purge time is the time it takes to remove excess precursor and gaseous chemical products.
In a closed-loop system, the simulation performs an experiment, gets the results, and feeds it to the AI tool. The AI tool then learns from it or interprets it in some way, and then suggests the next experiment. And this all happens without human insight.
The lack of human involvement cuts down on the time it takes to test each combination of materials.
All of these algorithms provide a much faster way of converging to optimum combinations because you are not spending time putting a sample in the reactor, taking it out, doing measurements, etc., as you typically would today. Instead, you have a real-time loop that connects with the reactor.
The expert system algorithm was developed fully in-house at Argonne National Laboratories, and the Bayesian approach was built using open-source tools like the scikit-learn Python library.
The experimental demonstration has been done in our custom reactors at Argonne, which gave us the possibility to tinker with the software controlling the deposition.
By utilizing all three AI techniques in their simulated system, Argonne researchers were able to measure film growth in real time after each cycle by forming a closed-loop system that automates algorithm optimization. According to the researchers, techniques can reduce the turnaround time to just a few minutes, so at least one order of magnitude time reduction. This was the first study to show how thin film optimization can work in real time using AI. However, the benefits of the closed-loop process in optimizing and automating ALD could be applicable to certain organizations in the microelectronics industry moving forward.
Our approach will be more valuable for those companies in need of establishing new processes. This includes companies supplying deposition tools for fabs, which have to constantly adapt and respond to their customer needs. The advantage of our approach is that it can be adapted to work with commercially available and off-the-shelf hardware. Anything that we've done is within reach of existing tool manufacturers.
Thanks for listening to this edition of Embedded Insiders. For daily news, videos, and podcasts, visit our website, embeddedcomputing.com.